All right, so good afternoon. Welcome everybody to the class. Recording is turned on, so you can write your name at this point if you want to be given data reimbursement. So write your name into the chat now or at any time during the class. Okay, it's good to see everybody back. I hope you all had a good Thanksgiving. And yeah, so today I want to finish this unit on word problems, and then we're going to move to talk about combinatorics and probability. And combinatorics often is in probability or often in the form of word problems also. So we're going to spend some time with that. Okay. So I know it's been a little while, and the homework was pretty challenging. I didn't receive any solutions in over the chat. Okay, so I didn't receive any solutions to the homework problems, so maybe we should go over them somewhat slowly because these are some challenging word problems, but at the same time, they can be solved with the exact same methods that we have basically for every word problem. It's just a question of going slowly and being patient for how they work. Okay, so thank you again for coming, and let's go get started so that we can finish on time. All right, so let's just recall how do we do these word problems? Oh, sorry. Hi, Prince. How are you? You seem frozen. I'm not getting you. I think your signal is cutting out. The network may be bad. Okay, but I see that you're here, so there you are. Okay, you're moving again. Okay. Welcome, Prince. Okay. Okay.
Okay, so
Hi. Okay, let me mute everybody. Okay. So remember with these word problems that often the math is not that complicated and all of the real work is in setting the problem up, right? So we have this method that we've been using called Keska. So key, equation, solution, check, and answer. It's all these steps that you can use for any word problem. And this is just as a review. In the key step, we write down our variables and what quantities they correspond to. Maybe there's one variable, maybe there's two or more. In the equation step, we set up one or more equations relating all of the variables. In the solution step, you solve the equation. In the check step, which we sometimes do and don't always do, you plug in your solution to the original word problem to make sure that it's correct. And then once you've done this, you have your answer. So these five steps that you can basically use for any word problem. And you may have your own method. A textbook may have a different method inside it, but they're all pretty equivalent, and this is what we're going to use in the class today. Okay, so if you remember, we started 3 weeks ago with some very, very basic word problems that were easy to set up and to solve. Okay, and now we have some more complicated ones, but they can still be done using the exact same method. Okay, so here's the first exercise that is a little bit complicated. So let's read through it slowly. Okay, so in a 10-mile bicycle race, Elijah covered the first 2 miles at a constant rate. He then sped up and rode his bike the last 8 miles at a rate that was zero point 0.5 miles per minute faster. Okay? Elijah's overall time would have been 2 minutes faster had he ridden the faster pace the entire time. What was his average speed for the whole race? Okay, so not that easy a question, certainly not something that you can solve in your head. But with our method, we should be okay, right? So we just go through the method, right? So the key. Well, I gave you a hint that basically says the key. Let X be Elijah's speed for the first 2 miles. So key X is going to be, what am I doing? What's happening here? No, 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 no. Okay. See, X equals Elijah's speed for the first 2 miles. It's Elijah's speed for the first 2 miles. And then what else do we need? Well, we know the last 8 miles, the rate is zero point 0.5 miles per minute faster. So I'm just going to write this as X. So maybe I should say this is in miles per minute. Miles per minute. And then so x plus 0.5, this is going to be equal to Elijah's speed for the last 8 miles. And this is also going to be in miles per minute. Okay. So this is basically it. This at least is only going to have one variable, right? Because we know how long the race is, and we have all of the information we need. The only thing that we need is to calculate what his speed is. Ultimately, we're going to need the average speed. So there's going to be an extra step to be able to do this, to be able to do this average speed. But for now, we're going to let this we're going to first calculate the speed for the first 2 miles and for the last 8 miles, and then as the hint says, after you solve for x, then we can calculate how long the race took and then calculate the average speed. Okay, so is everybody with me up to this point? Yeah. Okay, so now's what I think is the most important step of any of these word problems. So we have the key, and now we have the equation. So we need to use information given to us in this problem to set up an equation. Okay? So what is the actual information that the problem gives us? Well, it says Elijah's overall time would have been 2 minutes faster if he had ridden the faster pace the entire time. So basically, there is how much time it actually took versus how much time it would have taken at the faster pace. And we need to compare those two and show that one is 2 minutes faster than the other. So, does anybody want to try setting up an equation that's actually going to compare these two things? That's going to be an equation in terms of x. All right, anybody want to try?
Am I clear?
Yes. Okay, Linford?
All right. So in setting the equation,
Mm-hmm.
I did a stop, and I want us to look at is 2 over x
Okay.
plus 8 over x plus 0.5.
Yep. Mm-hmm.
8 over x, okay, minus
Mm-hmm. So,
10 over x plus 0.5
mm-hmm.
is equal to. That was what I did. I don't know whether I'm right.
All right. So it's almost right. So this is what Linford has, right? So this is what is this speed for the first or sorry, this is the time right over here. This is the time for the first 2 miles, and this is the time for the last 8 miles, right? Because this is a speed divided by distance equals time, right? Speed divided by distance is time. And then over here, we have this would be the speed at the faster pace. Oh no, this is right. This is right. So sorry, time at faster pace. No, this is exactly correct. Sorry. So this is the time at faster pace. Okay. Oh, okay. So this is the time at faster pace. And right, so what Linford has is that this is the total time it actually took. This is how much time we would have at the faster pace. And the difference between these two things should be two. Exactly. So this is great. Okay, so this is exactly the correct equation to set up. Um, so thanks, Linford. Does anybody have any questions on why this is correct? Okay, good. All right, so no questions. So the first thing we can clearly simplify this. So I'm gonna write on a new page. I'm just gonna copy down the equation. So this gives us 2 over x plus 8 over x plus 0.5 minus 10 over x plus 0.5 equals 2. We can simplify this, right? The 8 over x plus 0.5 minus 10 over x plus 0.5 is 2, is minus 2 over x plus 0.5 equals 2. And if we want to, we can simplify these twos into ones, but it might actually not be easiest to do this. So please elaborate on how we got this, right? Okay, so what is this 2? I'm going to try to write this down. This 2 is a speed. Sorry, this 2 is a distance. This 2 over here, 2 over x, this is a distance, right? And this x over here is a speed, right? This is x is Elijah's speed. This is what we set it equal to. So we have a distance divided by a speed is equal to a time, right? So you're doing a distance of 60 miles at a speed of 30 miles an hour. That takes 2 hours, right? So distance over speed is time. So this is the amount of time that it takes to cover the first 2 miles. Over here, this is the amount of time it takes to cover the last 8 miles. And then what does the question say? It says the time would have been 2 minutes faster had he ridden at the faster pace the entire time. So if the entire race is 10 miles and he's going at the faster pace, which is x plus 0.5, then the total time at the faster pace would have been 10 divided by x plus 0.5. So we have the time that actually happened minus the time that could happen if he was going faster. And we say that that amount of time is 2 minutes. That's that difference. Okay, so this is set up exactly correctly. Is that okay, Armstrong? Okay. Okay, so let's look back. I'm just copying this equation and then I just simplified the equation a little bit. So to solve this, what do we do? So this is the, I should say this is the solution step. Right. Well, we have these x's. Why the subtraction? So the subtraction, because we say that the time, this time is 2 minutes faster than this time, right? So the difference between the actual time and the hypothetical time, if he's going really fast, that difference is 2 minutes. That's why we have subtraction, right? This is the longer time. This is the shorter time. And the difference between the longer time and the shorter time is 2 minutes. So one minus the other equals two. That's why we have the subtraction. Okay, because it's this word faster, right? That's telling you that the difference between one time and the other time is 2 minutes. It's this difference. Okay. Okay, great. So 2 over x minus 2 over x point zero 0.05 equals 2. What we can do is we can multiply both sides of this by x times x plus 0.5. Okay, we multiply it by that. That way we'll clear the denominators. So if we multiply this first term by x times x plus 0.5, the one x cancels out with the x down here, and we're left with 2 times x plus 0.5, and then minus, we have here the x plus 0.5 cancels out with this x plus 0.5, and we're left with 2x. And then we have that this equals 2 times x plus 0.5. Okay. So now this is really just simplifying, and we'll end up with a relatively simple quadratic. So this gives us 2x plus 2x, and 2 times 0.5, that's 1. So 2x plus 1 minus 2x equals, and now we have to do the same thing, 2x times x and 2x times 0.5. So that's going to be 2x squared, and then plus what's 2x times 0.5? That's going to be x. Okay, so this is nice over here. We have a 2x and a 2x that cancel each other out, and we're left with 0. If we move the 1 to the other side, 0 equals 2x squared plus x minus 1. So these numbers are small enough that you can probably just factor this by sight if you want to. But we can also do our, just to recall this, remember we had this AC method that we talked about last time. So we want to find two numbers that multiply to minus 1, sorry, that multiply to minus 2, that's A and C, and then add to 1, which is the coefficient of x, right? They want them to multiply to the product of the first coefficient and the last coefficient and add to the middle coefficient. Well, that's pretty easy to see, right? So these two numbers that multiply to minus 2 and add to 1 are just 2 and minus 1, right? You can do that with trial and error, with guessing. And so then remember what we do with the AC method. We have that 0 is then equal to 2x squared. We take our 2 and our minus 1. So we add 2x, subtract x, and then we have our minus 1 over here, right? This is the our x, and we break it up. Right? So we do this AC method, we break up this x over here. Okay, so the x becomes a 2x and a minus 1x. And you see, once you have this, then the factoring becomes easy. So this 2x squared plus 2x, you can write that as 2x times x plus 1, and then minus x plus 1. That's what this minus x minus 1 is. That's minus x plus 1. And this, if you want, you can factor out an x plus 1. So that's x plus 1 times 2x minus 1. And so this finally leaves us with, if 0 equals 2x minus 1 and x plus 1, this gives us that x is equal to 1/2 or x is equal to minus 1, right? Because either 2x minus 1 equals 0, which would give you x equals 1/2, or x plus 1 equals 0, which would give you x equals minus 1. But remember what x is, right? You always have to remember your variables, right? So you've solved this equation, x equals 1/2 or x equals minus 1, but x here is a speed. It's not just a variable. It's a variable that represents something. And a speed is positive, right? He's doing the race, he's moving forward. His speed is going to be positive. So what that means is that we can't have a negative answer for x. So we reject this negative solution, and we're left with x equals 1/2, right? So x equals 1/2 is our solution here, but it's not the final answer for the problem, right? Because the problem asked what's the average speed. So we still have something to do here. Okay, so are there any questions so far about how we, what we did for this equation and how we solved it, how we set it up and how we solved it?
I'm a bit
Yep.
late, but I think I got a serious problem with the setup.
Okay. What is the problem?
Uh, the
Should I go
start
back
of the
here?
pro, the start of from the beginning. I wasn't part of it, so I got lost in between. The 2x minus 2 all over x plus 0.5 equal 2. That's why I got lost.
Right. So we set this up because basically these first two terms here represent how much time it took to finish the race, and the second term here represents how much time it would have taken if Elijah rode at the faster pace the entire time. Okay?
Okay.
And so the setup is that the difference between these two things is 2.
All
Okay?
right. Together.
Is that okay?
Yes.
Okay. Okay. So everything's okay. So we have x equals 1/2. Great. So x is equal to 1/2. That's fantastic. Good. So let's go back to the problem. So what does the problem say? It says, what was his average speed for the whole race? Okay. So what was his average speed for the whole race? So maybe before we do that, we should check that this x works, right? So it's saying the overall time would have been 2 minutes faster if he rode at the faster pace the entire time. So let's actually check this. I'm going to add a new page. This is the check before we get the answer. Okay, so check. We have x equals 0.5 miles per minute. Okay, so actual pace is we have 2 miles times 0.5 miles per minute. Sorry, 0.5. I'm sorry, what do I want to say? Sorry, 2 miles divided by 2 miles divided by 0.5 miles per minute plus 8 miles divided by, then at the faster pace, right, is 1.0 miles per minute. What does that equal to? Well, that's going to be 4 minutes plus 8 minutes, and that equals 12 minutes, right? And then if at faster pace, then we would just have 10 miles divided by 1.0 miles per minute, and that's exactly 10 minutes. And so that's good. So that's 2 minutes faster, which is exactly what we want. So that's a check. Okay, so that works fine. Okay, so that's at the faster pace. Okay, so that's our check. So now what's the answer? I'll do one more page for the answer. So the answer is what? Well, we want the average speed. Well, how do we calculate average speed? The average speed is equal to the total distance over the total time. Well, the total distance we know, that's 10 miles. That's how long the ride is. And the total time we also know, it's 12 minutes. This was at the actual pace that took 12 minutes. So the total distance over the total time, this is equal to 10 miles over 12 minutes. And so if we want, we can say that this is equal to 5/6 of a mile per minute, or roughly 0.83 miles per minute. Okay, so either of these is a correct final answer. Right? So you have to remember in a question, and this is particularly important on something standardized like the WAS, that if you have multiple choices, you need to answer what the question is asking. So you can solve a problem completely correctly, set up the key, solve the equation, do everything. You solve for your variable x. But if your variable x is not what the question is asking for, then it's not going to be the right answer. So in this situation, it was useful for us to set the question up with x being Elijah's speed for the first 2 miles. But the question doesn't ask that. The question says, what is the average speed for the whole race? So even after you solve for x, you still need to do one more step to calculate the thing that the question actually asks for, which is what is the average speed for the whole race. Okay, so in our case here, the average speed for the whole race is going to
Hello?
be 5/6 of a mile per minute.
Hello, sir.
Yes, Rush?
Yeah, I have a question on the problem we have, which is what we have and the in 2 minutes fast how the and the object move faster. We have 10 miles per hour, 10 miles per minute.
Mm-hmm. 1.0, this is 10, it's a 1.0 miles per minute. There's a decimal
Oh,
point here, sorry.
okay, okay. I just see
Yeah.
it.
Okay.
Okay.
Sorry.
Uh,
Yeah, so this decimal point right here. Okay, other questions? Okay, let's move on to the next one. Okay, this next one's also going to be a little bit complicated, so I don't want to set it up myself. So when there is no wind, a plane traveling at a constant rate can cover the 1,000 kilometer round trip distance from A to B and back in 10 hours. If the wind, it's a pretty slow airplane. So if the wind blows from A toward B at k kilometers per hour, then the trip is sped up by 25 minutes. And then we want to find k. So again, these questions always look a little hard until you just break them down into their little pieces and set them up. So what should we set what should we set up for the key? And it's okay if we spend a lot of time on this because I want to make sure these word problems are really solid. So what would be a useful variable to introduce here?
Yeah, hello there.
Yes, hello?
Yes, hello. Yeah, so inserting the key, what I did,
Mm-hmm.
I have from A to B, which is the ground speed,
Mm-hmm.
I set it as 100 plus K.
Okay.
Okay. And then from B to A, which is also the ground speed, I set 100 minus K. Then where I
Okay,
was, and
so
then I
so hold on,
then
hold on. Wait, wait. So how do you know that that's the oh, okay, yes, 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 yes. Okay. So we know that the ground speed, right. So key is going to be ground speed from A to B is going to be
to B.
100 plus K,
Plus K. Yes.
and
And
ground speed
speed from
from
B to A
B to A is
A
equal.
is 100 minus K.
Exactly. Right. And I
Exactly.
mean, the
Right. And I
reason we
mean,
know
the
this is that
reason
we
we know
know
this.
that if there's no wind, it does 1,000 kilometers in 10 hours. So the ground speed has to be 100 kilometers per hour if there's no wind. So it will get sped up or it will get slowed down, depending on which way it's going. Okay, great. Okay, so do you want to stay and do the equation also?
Yes, I want to provide the equation as well so that we
Okay.
can all look at it. Okay. All right. So for the first equation, means for the equation is 500 over
Mm-hmm.
100 plus K. 100 plus K. All right. Plus 500 over 100 minus K
Mm-hmm.
equal 100,000.
100,000? Sorry.
100,000. Sorry. There's 100,000, please.
Okay.
Okay. 100,000 over 10,000 minus K square.
Okay.
Okay. 10,000 minus K square.
Like this?
That's the equation I have. So we can look at it, please, whether I'm right.
Okay, so oh, wait a minute. Oh, okay. But this equation is just true, right? So you got this by combining these two fractions. How did you get 100,000 divided by 10,000 minus k squared? That's from you put these two fractions together with a common denominator?
Yes, yes.
Yes. Okay. So that's correct. But the problem with this is that this is not going to help you solve for k because the expression that you have on the left is always equal to the expression on the right, right? Because you got this expression from combining these equations and using math, right? So no matter what value of k you punch in here, you're going to get the same thing on both sides, right? So it's not going to help you solve for k. So I think, so this side over here is correct. And we want to know, what does this side represent? This side represents, right, time to do the round trip with wind, right? This is the time to do the round trip with the wind, right? Because we have 500 divided by 100 plus k. That's the time to get from A to B. And this is 500 divided by 100 minus k. That's the time to get from B to A, right? So it is true that when we solve our equation and we simplify this side, we're going to get this. But what we actually want to do with the setup is we want to use what the problem is telling us. So the problem says that this time should be 25 minutes faster than this time, right? So here, maybe we should use units. So what is this? This is kilometers per hour, and this is also kilometers per hour. So the time to do the round trip with the wind, what do we know about it? Well, we know that it's 25 minutes faster than the time to do the round trip without the wind. Okay, so the time to do the round trip without the wind is 10 hours. So the time to do the round trip with the wind should be 10 hours minus, and now you have to be a little careful. Our units are hours, right? Oh, okay, so I see that Abraham Borgon has an answer. I don't know if it's right. We'll have to solve it. But what we have here is 10 minus 25 divided by 60, right? Because this is time without wind. And this over here is 25 minutes faster. This is 25 minutes faster. Okay. So what we really want to set up as an equation is that this expression equals 10 minus 25 over 60. And then, as Linford did, you can combine these fractions, and that will exactly give the answer that he wrote down. So we'll combine these. I'll write down this 100,000 divided by 10,000 minus k squared. But before I do that, does everybody understand why this is the equation that we want to solve here?
I'm a little bit
Yeah.
lost over the left side of the question for Binda. The
Okay.
500 or 100 plus K, and the other 500 was 100 minus K.
Right.
I'm lost between them. I got the right side that you just did.
Okay.
How the
Okay, so we have our key, right? So the ground speed, this 100 plus k is the ground speed from A to B, and the 100 minus k is the ground speed from B to A, right? So what do we have here? 500 kilometers is the distance from A to B, right? Because it says 1,000 is the round trip. So 500 kilometers is the distance from A to B, right? So this here, it's kind of like the last problem. This is a distance, and this here is a speed. So if you do the distance divided by the speed, that gives you a time. So this
That is
first
correct.
fraction here is time from A to B.
I get it. It's clear.
Okay, got it.
It's
Right.
clear.
And then this here is time from B to A. So when you add them together, it's the full time for the round trip. So this time should be 10 minus 25 over 60, which if we want to make the numbers a little simpler, this is 10 minus 5 over 12, or you can make this, that'll be 115 over 12, if you want to combine them. Okay. All right, so let me write the equation on the next page. So we have 500 over 100 plus k plus 500 over 100 minus k equals what do we have? 115 divided by 12. So you could combine them, but yeah, I think it'll be easier if we do what we did in the last thing. We're going to multiply by 100 minus k and 100 plus k because this is going to clear the denominators. We multiply by the easiest function that's going to clear all of the denominators. So in this case, if we multiply by these, the first term, the 100 plus k, cancels with the 100 plus k, and we're left with 500 times 100 minus k. Similarly, here we have 500 times 100 plus k, and this should be equal to 115 over 12 times 100 minus k times 100 plus k. And now let's expand everything out. This should look familiar because it's exactly what we did the last time, right? So here we're going to have 500 times 100, so that's 50,000 minus 500k plus 50,000 plus 500k equals, and now here we have 115 over 12 times 100 plus k times 100 minus k. That's a difference of two squares. So we get 100 times 100, which is 10,000 minus k squared.
Hello?
Hello, yes?
Equation wow. Another form, you still have the as this equation, the first equation on my common degree, when you
Yep.
said 100,000 divided by 10,000 minus k squared equals to 115 over 12. You do it that way.
Yeah, that will work also. That will be fine. Okay, and so the good thing here is that we're actually going to have a pretty easy quadratic equation because this k term and this k term cancel each other out, this 500k and other 500k. And so what we end up with is just 50,000 plus 50,000, so that's 100,000 is equal to, well, we have 115 over 12 times 100,000. So I'll say 115,000 divided by 12 minus 115 over, oh, let's maybe instead of multiplying it out, let me just
Yeah,
write that this is, make it easier. This
simplify
is,
it for understanding
yeah,
sake.
let me just copy it for now. Right. And then it will be easier, right, which I think I heard, is to just multiply both sides by 12 over 115. Right. So that's going to give you 12 over 115 times 100,000 equals 10,000 minus k squared, or uh, the, hold on, now I am confused because I'm worried there's a sign error somewhere. I'm worried that this is going to not give any real solutions. So did I make a mistake somewhere? Have this equation 10 minus 5 over 12 is definitely 115 over 12. Okay. So it may be that, yeah. Okay, I see what's happening. I think I wrote this solution. I wrote this question wrong. So the way there's actually going to be no solution. So let's do that. Let's let's actually carry this out, right? So, um, so what happens here? We can get that k squared, if we move it to the other side, equals 10,000 minus 12 over 115 times 100,000. And if you do this with a calculator, what does this turn out to be? So 10,000 minus 12 times 100,000 divided by 115. This looks like it's about negative 434.78.
Negative 434.78
Right.
to 261. 261.
Yeah, to two decimal places. The point is, the number of decimal places doesn't actually matter, right? Because here we have k squared equals a negative number, right? So what this tells us here is no real solutions for k. All right. So no real solutions for k. And what does this tell us? So what's actually going to happen here? So this is it, right? I mean, this is the solution. The solution is that there are no solutions. Okay, there's no real solutions for k. And what this tells you is exactly, right? A wind blow. So as Linford writes, this is exactly right. So basically, if a plane is making a round trip, having no wind will always be faster than having a constant wind speed. Okay, whatever you gain from your constant wind speed helping you from your tailwind in one direction, you're going to lose more than that from the headwind in the other direction. Okay? So for this thing, we can't find k because the trip cannot be sped up by 25 minutes by there being a constant wind speed. So maybe another question that I'll ask that we won't do right now, but you can think about on your own is instead, oh, ooh, I didn't want to do that. Instead, what would k be if it slowed down, or if the wind, I'll say if, what would k be if the wind slowed down the round trip by 25 minutes? Okay, so this is a question that we're not going to do now, but it's something that you can do with a similar setup. So what we've seen basically is that, the wind can't speed the trip up by 25 minutes, no matter what the speed is. So is there a way that the wind could slow down the round trip by 25 minutes? Well, maybe there is. You'd have to solve an equation that's slightly different from the one that we wrote down. Okay? So any questions on this? There's not really anything to check because there's no solutions.
Taylor?
Okay. Yeah, question?
No, not question ready, man.
Mm-hmm. Ready. Okay.
I just wanted for you to give me a little hint on, maybe you want trying to download a book, maybe a page that you can get free books, the solution manual like that. And
Oh, so solution manual for the Art of Problem Solving, Volume 1 for the book that I sent out?
no, 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 not really. There's a book I want ready, but I don't. I try getting the solution manual, but it's no tough time because well, I use it because some books when you use credit card to get the books, and that's the reason why I ignore any was site
Mm-hmm.
and download it.
Okay. So maybe send me something after class on the chat and I will try
All right,
to see what I can find. so that I know what it is that you want.
Okay,
Okay.
okay.
All right. Okay. Okay. So homework exercise number 3. So we did this last time. So you've scored. We talked about inequalities a little bit last time. Remember, you can use Kesca for word problem equations, but you can also use it for inequalities, right? So here we have scored grades of 82, 76, 0, and 90 on the first 4 exams. So 0, I guess you missed the exam. So there's one more exam, and to pass the course requires an average grade of 70 on all 5 exams. And so the question is it possible to pass the course? Okay. So the setup here is relatively easy. So what's the key going to be here? Well, there's one more exam, right? That's kind of the only unknown. So let's let X equal to the score on the last exam. Okay, that's really it. So this is going to be a simpler equation than what else we have. So equation. Okay, so what's the equation here? Um, well, we want to know whether it's possible to pass. So this equation, which in this case is actually going to be an inequality, because you want to pass the course requires an average grade of 70. So that means to pass, you have to have at least a 70. So how can we set up an equation where the average grade is going to be at least a 70 and write this in terms of X? Can anybody set up an inequality? Okay, well, what do we have? We need an average grade of 70, right? So we want the average grade to be greater than or equal to 70, right? This is what the equation should be, right? The inequality should be average grade is greater than or equal to 70, right? So what happens here if the average grade is greater than or equal to 70, then we have, so what is the average grade? Well, we have scores of 82 plus 76 plus 0 plus 90 plus, well, there's a score on the last exam, right? That's X. And to take the average, we have to sum all of these up and divide by 5. And we want this to be greater than or equal to 70. Okay, so the solution, this is pretty easy to solve, right? I just multiply both sides by 5. I have 82 plus 76 plus 0 plus 90 plus x should be greater than or equal to 5 times 70 is 350. Let's just finish this on this page because this one is pretty easy. So what happens? 82 plus 76 is 158, plus 0 is still 158, and then plus 90 is 248. So we have 248 plus x is greater than or equal to 350. Not possible, right? So Harrison said, right, so if we now solve for x, this gives us that x is greater than or equal to 350 minus 248, which is 102. So assuming there's not any extra credit that, and the question doesn't say there is, right? Every exam is out of 100 points. That means in order to pass the class, at least officially, you would need to score at least 102 points on the last exam, and that's not possible, right? Not possible because X can be at most 100. Okay, so we had two instances where where we ended up without a possible solution. In one case, because there's no real number at all, but in another case, because the actual solution would have to be bigger than 102, which is not possible. Okay. All right. Any questions? Okay, so this one's relatively simple, but you still have to just set it up correctly. And I think I'm not going to do the check. Okay. So I'm just gonna leave this as the answer here. I'm not going to do the check for this problem. But if you wanted to do the check, you would just punch in 102 and show that that gives an exam score of 70. Okay. No questions on this? Okay, so let's move on. Okay, so I wanted to do this one example also that we didn't do last time. We had an inequality example left over from last time that we didn't get to do. So he said that the perimeter of a rectangle is 48 inches, and if its area is at least 135 square inches, what can we say about its width? Okay, so this is an example. It's really an algebra problem, but it's masquerading as a geometry problem. And when you have a word problem that involves geometric figures, usually it is useful to draw a picture. So that's maybe the first step before you do Keska is if there's a picture or a diagram to draw, you should draw that, right? Call it Keska. So here we have it's about a rectangle, right? And the rectangle has a length and a width. So what is our key? Well, our key basically comes exactly from the variables that we have. So our key is the length. Maybe I'll say let L equal the length of the rectangle. And we'll let W equal the width of the rectangle. Okay. So that's pretty easy. L is the length of the rectangle, W is the width of the rectangle. Not really much else to say. Not X. So, okay, so now we have equations. We've got two variables here, so there's probably going to be more than one equation. So what equations do we have that can, equations or inequalities? There's actually in this case going to be one equation and one inequality. So what can we write down in terms of these variables L and W? What do they have to satisfy? Anything? Well, okay. So there's two things, right? There's two facts in this problem, right? Yes. So the first thing is yes, we can say 2L plus 2W equals 48, right? The perimeter of the rectangle is 48 inches. So we have 2L plus 2W equals 48, right? Because this is the perimeter. L plus W plus W. This is going to be 48. Okay? Great. So that's the first equation. And now we have the second equation. So the area is at least 135 square inches. So what do we need to write for that equation? All right, so look at the size of the equations. The equations, okay, so that's exactly right. So L plus W, that's exactly the perimeter, and that's 48. But we also have the area, right? And so the area of the rectangle, right, is L times W. And we want that to be at least 135, right? So this is, this
Yeah.
first equation is perimeter equals
Yeah.
48. Yes. And the second equation, yes, so that's right, it's Armstrong. And the second equation is area is at least 135. Yes, question?
Hello.
Yes, Rush?
Hello.
Yep.
Yeah. Pertaining the other question where you're asking for the average speed. One way to please go back a little bit. Something I want to ask from there.
Sorry, can you say that again? I didn't catch it.
I said that the first question where you asked for what how many students I know pass, you was
Oh yeah,
asking
this
a
one.
little bit.
Yeah, so what grade do we need to pass? Yeah, so for the average,
Yeah,
it's
yeah, yeah.
mhm.
Yeah, because I was not getting the internet is breaking in. That's a problem.
Oh,
Can you
okay,
go back
yes.
to it, please?
Okay, so I can just go back to this, sure, if you want to look at it quickly. Basically, when you set up the inequality, if you solve it, you get that the score has to be at least 102. And since the exam is out of 100 points, you can't get 102, and so it's not going to be possible to pass.
I'm not seeing it on the screen.
Oh, should be on the screen. Are other people seeing it on the screen? The exam question?
For me, I'm
Should
not seeing it. Okay, I
Oh,
see it now.
that's Oh,
It's
you're
I
seeing it
seen
now.
it.
Okay. Yeah.
Oh, yeah, 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 yeah. Okay, okay. I understand. Thank you.
Okay, you're welcome. Okay. Why the use of greater than or equal to sign? Okay, that's a great question. So from Prince. So we use the greater than or equal sign because of this word at least, right? So when you say something is at least something else, that means greater than or equal to, right? If it said that the area is greater than 135 square inches, that just means using the greater than sign. But at least means the greater than or equal. Because if the area is exactly 135, that's okay, right? The area is 135, that's okay. It's just if the it doesn't have to be strictly greater than 135. It's okay if it's exactly 135 because that's also included in at least. Okay. Okay, so these are our equations. It's kind of a little unusual. We have one equation and one inequality, right? We have one equation and one inequality. But that's okay. Ultimately, we're going to want to solve the inequality. So what we're going to need, the question is, what can we say about the width, right? So ultimately, we want to say something about W, about the width. So what we're going to need to do is use our equation that lets us make a substitution so that anytime we see an L, we can write a W instead. So we'll do this on the next page, but let me write the strategy is use the equation to substitute for L in the inequality. Okay, so we're going to use the equation to substitute for L in the inequality. Okay. 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 So let me get a new page. I'm just going to write this down. So we have, I'm just going to copy the equation. So 2L plus 2W equals 48. Equals 48. And also L times W is greater than or equal to 135. 135. Okay. So we want to substitute for L, get it all in terms of W. So 2L equals 48 minus 2W, or dividing by 2, L equals 24 minus W. So if we substitute, every time we see an L, we write instead 24 minus W. So 24 minus W times W should be greater than 135. So let's simplify this out. This tells us that 24W minus W squared is greater than or equal to 135, right? I'm multiplying everything by the W. Or maybe let me do it the other way. Let me say I'm doing this W times this W and also times the 24. Okay. And now I can move everything to this side. Adding and subtracting things does not change the sign of an inequality. So I can add W squared to both sides and subtract 24W from both sides, and everything's going to stay the same. I still get 0 is greater than or equal to W squared minus 24W plus 135. Okay. Okay, and so now we can factor this, right? So this is a quadratic, so we can factor it, and we need two things that add to minus 24 and multiply to 135. If you do a little bit of trial and error, it turns out that this factors into W minus 9 times W minus 15. Okay, so this is our solution, by the way. I should just say solution. Okay. So W minus 9 and W minus 15, and we want this quantity to be negative. Okay. So what do you do when you're solving a quadratic inequality? If this was a quadratic equation, if we had 0 equals W minus 9 times W minus 15, if that was equality, then we would just say, okay, either W minus 9 equals 0 or W minus 15 equals 0, which would be either W equals 9 or W equals 15, and you'd be done. But here we have an inequality. So the choice of possible W's is going to be in some kind of range. And so maybe I'm going to give this on a new page. So let me just copy this onto a new page. So here I have 0 is greater than or equal to W minus 9, W minus 15. Okay, and the technique that I like to use here is to use the number line. And with the number line, I'm going to mark the equality solutions. Okay, so I'm going to draw a number line here. I'm going to mark the solutions where you have equality. So you have equality here at w equals 9 and equality again at w equals 15. All right. And then I'm going to test each of these ranges. I think of these marks as dividing the number line into regions, into ranges. And now I'm going to look at each range separately. So over here, when x is bigger than 15, I have, sorry, when w is bigger than 15, right? This is the w line. So if w is bigger than 15, then w minus 15 is positive, and w minus 9 is also positive. So the product is going to be positive. So I'll write this as positive times positive equals positive. What about when you're between 9 and 15? Well, if I take some w between 9 and 15, then w minus 9 is positive, but w minus 15 is negative. So I'm multiplying a positive by a negative, and that's equal a negative. And then lastly, what happens if w is less than 9? Well, then w minus 9 is negative, and w minus 15 is also negative. So I have a negative times a negative, and that's equal to a positive. And what do we want? Well, we want this thing to be negative or 0, right? So I'll say by looking at the number line, we see that the right-hand side, I'll abbreviate that at RHS, is less than or equal to 0 exactly when W lies between 9 and 15. And so exactly when W is between 9 and 15. And so this is what we want, right? We want the area to be greater than or equal to 135. That's going to happen exactly when the width is between 9 and 15. All right, any questions? Okay. All right. Everybody's happy with this? Yeah. So when you have these quadratic inequalities, you usually need some sort of graphical method for solving them. And the method that I find the most useful is to draw a number line and try to figure out, are things positive or are they negative on each different part of the number line? And that's going to give you a good technique for solving these graphical inequalities. Okay, so any questions on any of these examples? I know we spent a long time on this, but I wanted to make sure that the word problems are really, really solid before we move on to the next unit. Okay. Okay, so we're going to have a new topic, although we really only have 20 minutes, so we're not going to go too deep into the new topic today. So So we'll spend more time on it next week. So the new topic that we're going to do is combinatorics and probability. So just to define these words, combinatorics is the study of counting things, trying to figure out how many objects there are that satisfy some certain property. And probability is the study of how likely events are to occur. Okay? And these two topics are closely related because often, in order to calculate the probability of something happening, you have to count up all the possible ways that it can happen. So you count up all of its possibilities. And so today's class will focus on combinatorics, and then next week we're going to apply it to probability. But actually, since we're getting such a late start on this, I think next week is going to be mostly combinatorics as well. Okay, so probability will probably have to wait until the week after. Um, so in both combinatorics and probability, a key idea is independence. And this is, how every time we do a unit this semester, I'm trying not to just teach the unit, but I'm trying to give one key idea to think about when you're doing your pedagogy, when you're deciding to teach. And I think combinatorics and probability is something that people have a lot of trouble with, just like word problems. And I think part of it is just because there's so many different types of problems and so many different ways that a problem can look. And just like with word problems with Keska, in combinatorics, if you keep the idea of independence in mind, then that will let you solve almost all of the problems that you could possibly come across. So the focus that we're going to have is independence. Okay. And turns out that just thinking about this idea can get us pretty far. Okay. And I'll say a reference for these topics. So this textbook that I sent, The Art of Problem Solving, Volume 1, chapters 25 and 26. So 25 covers combinatorics. And chapter 26 here covers probability. Okay, so these are nice brief references. I think each chapter is only about 10 pages long. So it really has lots and lots of types of problems and lots of good examples here. Okay, so I recommend checking out chapters 25 and 26 if you wanna an exposition for combinatorics and probability. Okay. All right. So what is the overview of independence? What do we mean by independence? So when we say that two events are independent, it roughly means that they do not affect each other, right? So what does this mean specifically in combinatorics? Well, in combinatorics, usually you're asking how many ways can something be done, or how many objects are there that satisfy some certain property. Okay? And usually this can be broken down into whatever you're trying to count. You try to count smaller pieces that are independent of each other. And you figure out the total number of ways by figuring out the ways of doing each little thing and combining them somehow. So the most basic example of this is that if you have four shirts, and we're going to call them A, B, C, and D, and three pairs of pants, we're going to call them X, Y, and Z, then how many ways can you choose a shirt and a pair of pants? And the answer is, well, you've got four choices for the shirts and three choices for the pants, and the number of ways that you can combine them is always the product. So that's going to be 12. And you can see this visually, right? Here are all of the 12 combinations, right? You can have shirt A with pants X, or shirt B with pants X, shirt C with pants X, and so on. Shirt A with pants Y, B with Y, A with Z, B with Z, and so on. So just from this picture right here, very, very clear that if you have two choices to make, and you make one choice one way and you make the other choice another way, then the total number of ways that you can make both choices is going to be the product of the number of ways to make the first choice and the number of ways to make the second choice. Um, so, so this is this particular very basic example with shirts and pants, but this is the fundamental principle of combinatorics. Okay, so we can call this the main principle of counting, or independent events, or you can call it the multiplicative principle. So, say an event is conditioned on making a number of independent choices, and for each choice, there are a certain number of options. So keep in mind this question. You're making two choices here. You're choosing which shirt to wear, and you're choosing which pair of pants to wear. Okay? And these choices are independent of each other. I'll say what I mean. So it says, well, the total number of possible choices in this case is the product of the number of choices at each step. But what does independent actually mean here? Independent means that the number of choices at each step is not affected by any particular choices that you've made at the previous steps. Okay? So in this previous problem, no matter what shirt you pick, there's always going to be three choices of pants available. It doesn't matter whether you pick shirt A or shirt B or shirt C or shirt D. In all cases, there's going to be three pants choices available. Or you could do it in the other order. You could pick whatever pants you want, and no matter what pants you pick, there's always going to be four shirt choices, right? So if we had made the question more complicated and said, okay, well, certain shirts don't go with certain pairs of pants and you can't pick them together, then the question gets more complicated. You don't have independent events anymore. But for this case, when it's simple, you have independent events. And one of the things that we'll see in some of our examples, we'll probably only get to do one or two examples today, but we'll do more examples next time, is that in order to actually make your choices independent, you sometimes have to be smart, clever about what order you make them in. So for this first basic problem, it doesn't matter. You can choose your pants and then your shirt, or you can choose your shirt and then your pants. Makes no difference. Everything is totally independent. But sometimes you need to make a choice. Okay, so what's the most basic example? So a lot of the challenge in combinatorics is you're trying to count something and you want to know, are the different events or the different choices that you're making actually independent or not? And if they are, then you can solve it by doing this using this multiplicative principle that you multiply all of the possibilities. Okay, so example one, basic example. In how many ways can five differently colored footballs be given to five different children, one football for each child? So I find with these combinatorics problems, I like to draw just a little diagram. So I have these five children. Maybe we'll give them names. We can call them A, B, C, D, and E. Okay. And we want to know, I've got five footballs and I'm going to give one to each child. Okay. So the question is, and how am I going to do this? Well, there's a whole lot of different things to do, but basically, I'm making five different choices. I'm choosing which football am I going to give to A, and then which football am I going to give to B, and which football am I going to give to C, and which football to D, and which football to E, right? Those are my choices. So the question is, how many choices do I have, for instance, to give a football to A? So how many choices do I have for giving the first football away to child A? Well, I've got five, and I can give any of them to the first child, right? So that's five choices. So now, so this is going to be, I'm going to write here child, and I'm going to write here number of choices. Okay, these are not fractions. These are just like slots. I don't mean 5 over A. Don't read this as a fraction. I'm saying you got child A, you got five choices. Okay. So now that I've given one to child A, how many choices do I have left for child B?
Should we say four?
Four, exactly. Right. So four for B because one's already been given to A. Um, and then now that I've given one to A and one to B, how many choices are left for C? Three, exactly. And then pattern continues, two for D, and then there's only one left to give to E, right? And here we've got multiplication, 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 multiplication. This is the multiplicative principle. Multiplicative principle. That's why I have all of these multiplication signs here. And if you do 5 times 4 times 3 times 2 times 1, you can do this and you get 120. Okay. So I mean, this is not that hard, but I want to spend a little bit more time thinking about what's actually going on here. Because you could argue, if you were in an arguing mood, you could say, wait, but these things are not independent, right? Because when I give a football to A, I can't give that same one to B. So what I do with A affects B. And when I give something to B, then I can't give that to C anymore. So this is all, so each time I make a choice, it's affecting my later choices. So how can you say that these things are independent? They seem to depend on each other. And for the answer, we need to go back to what we said over here, which is that what does independent mean? It means that the number of choices at each step is not affected by any particular choices made at the previous step. So let's say my footballs are whatever, I'll just give 5 colors: white, green, yellow, blue, and black. Okay, so let's say these are my 5 footballs. They're white, yellow, green, blue, and black. Well, let's say I give the white one to child A. Well, then there are 4 choices left for B. Let's say instead I give the yellow one to child A. Well, in that case, there are now still 4 choices left for B. They may be different choices, but it's still the same number of choices. And if I give the black one to child A, then there's still 4 choices left for B. Right? So what I'm going to say here is that the events are what's going. The events are independent because no particular choice I make, no particular choice I make for one child affects the number of choices for a later child. Right? If I say the way I'm going to do this is I'm going to give one to child A and then one to B and then one to C and one to D and then one to E, then I'm going to say that no matter which one I give to A, I'm going to have the same number of choices for B. Okay, no particular choice I make can change that. Okay, so that's why these events are independent, even though, of course, if I give the white football to A, I can't also give it to B. But it's still independent because whether I give the white or the black one to A doesn't make any difference for how many choices I have for B. It may affect which choices I can make, but it doesn't affect how many choices. Okay? All right, so any questions on this? Okay, so there's no questions on this. I'm probably going to stop a little early today because I don't want to get into the next. I don't want to get into the next examples. So we'll talk about this. We have a bunch of examples that we're going to do next time. And we're going to talk about, we have more examples. How do you deal with non-independence? Some other non-independence things. We're going to talk a little bit about permutations, or talk about combinations. So we're going to do this all next time. We have these homework exercises. You can try them if you want. You can try these. You can try these if you want. But I haven't really told you how to solve them. So you can try these if you want. Some of them may be a little bit of a challenge. But they can all be solved using this independence principle. Okay, the first couple are not so hard, and then the last one may be a little bit harder. And so I'll say for next week, we're going to turn our attention to probability, but probably not. I think we will do because we didn't get to, because we spent so much time on the equations today. Next week, we will do more combinatorics, including permutations and combinations. Okay, so we're going to do more combinatorics, including permutations and combinations. And when I send out the notes, I won't send out this extra stuff that we're skipping. Okay, I'll send out the I'll take some pages out of the notes before I send it out. Okay. So we will meet next week. Last week was off, but next week we're going to meet as normal on the normal Thursday at the normal time. Are there any questions, at least on this? Any questions on this example or on the idea of independence before we break? Okay, so if there's no questions, then I'll talk to Sanjay also about what's going on with the certificates. And for everybody who had a mistake on their certificate, Mr. Randolph has the corrected ones, and he says that he knows somebody who's going to Liberia in early December. So hopefully that person will carry the certificates with them so that they can get to you for the 4 or 5 people for whom there were some mistakes. Okay, so if there's no further questions, then thank you all for coming as always. Please, if you didn't yet put your name into the chat, please type it in now, and I will see you next week.
Thank you, Dad. Thank you so much.
All right, you're welcome. Okay, and I'll send out the notes and I'll send out the video when, later on today.
Okay.
Okay. Okay, great. Okay. Have a good night, everybody.